In this session, let us consider the derivation of moments of Pareto distribution. We know that Pareto distribution has probability density function f of x equal to alpha beta raised to alpha divided by x raised to alpha plus 1, where x is greater than or equal to beta. Consider rth moment about origin. By definition, rth moment about origin is expectation of x raised to r, which is equal to integral beta to infinity x raised to r into f of x dx. Substituting the probability density function, we will get it as expectation of x raised to r equal to integral beta to infinity x raised to r into alpha beta raised to alpha divided by x raised to alpha plus 1 dx. On simplification, we get expectation of x raised to r as alpha beta raised to alpha. They are constant, so it is taken outside the integral. Then integral beta to infinity x raised to r minus alpha minus 1. So the denominator comes to the numerator and also r is added to that. Now we know that integral of x raised to n dx is x raised to n plus 1 divided by n plus 1. Applying the limits, we get expectation of x raised to r is equal to alpha beta raised to alpha x raised to r minus alpha minus 1 plus 1. That is x raised to r minus alpha divided by r minus alpha beta to infinity. When x is replaced by infinity, we know the convergence condition for it to exist, it should come in the denominator. So r minus alpha, the power of x, should be negative for x raised to r minus alpha to come to the denominator, and so as infinity extends to infinity, the 1 by x raised to r minus alpha will converge to 0. So x raised to r minus alpha r minus alpha should be negative. That is, r should be less than alpha for convergence. The rth row moment exists if r is less than alpha. So, alpha should be greater than r. That is the condition. So, applying that condition, we will get it as first term becomes 0. So, substituting, we will get expectation of x raised to r equal to alpha beta raised to alpha minus beta raised to r minus alpha divided by r minus alpha. So, if we will get it as, finally we will get it as expectation of x raised to r equal to alpha beta raised to r divided by alpha minus r, where r is less than alpha. When r equal to 1, we get expectation of x, that is arithmetic mean. Expectation of x is alpha beta by alpha minus 1. The condition alpha should be greater than 1. Alpha should be greater than 1. Second moment exists is if alpha greater than 2. Expectation of x square equal to alpha beta square divided by alpha minus 2. Now we can substitute this expectation of x and expectation of x square in the variant formula of variance for finding variance. Variance of x equal to expectation of x square minus expectation of x the whole square. Finally, after all numerical calculation, what will we get? Variance of x equal to alpha beta square divided by alpha minus 1 whole square into alpha minus 2. So, for variance to exist, alpha should be greater than 2. Similarly, we find third moment and also fourth moment. For third moment to exist, alpha should be greater than 3. For fourth moment to exist, alpha should be greater than 4. So, higher moments exist only if alpha is large enough. We have already studied that for small alpha, heavy tail is heavy tail is there for Pareto distribution. Moments diverge. Large moments exist only if alpha is large enough. So, next we will consider the skewness and kurtosis. From this raw moments, we can calculate the central moments. So, after that, calculating the skewness and kurtosis, we already know that the skewness and is positive always for Pareto distribution. Skewness is positive or right skewed. Long right tail and large values occur occasionally. And we know that for Pareto distribution is leptokurtic or high kurtosis, heavy tails, and extreme values are more likely for Pareto distribution than normal distribution. As alpha decreases, skewness increases, kurtosis increases, distribution becomes more heavy-tailed. As alpha increases, distribution becomes more stable, approaches less extreme behavior. So, we have discussed about the positive skewness, leptokurtic behavior of Pareto distribution, and the skewness exists only if alpha greater than 3, kurtosis exists only if alpha greater than 4, and we have studied about the parameters of Pareto distribution, alpha and beta. Alpha is the shape parameter, beta is the scale parameter, and also I will show probability density function curve for different alpha. See here, there I have created plots on Python using Python code. There are subplots for alpha equal to 1.5. This is the subplot. For alpha equal to 2, this is the subplot with much lighter tail. This is more heavy tailed. When alpha equal to 3, the tail becomes bit more lighter. Alpha equal to 5 means the tail is very not at all heavy. Look at this. So extreme values will be very less. So when our data contains extreme values, for heavy tail there will be more extreme values in data. For light tailed there will be less extreme values. So these are the things that basic facts that we should remember while studying Pareto distribution. So we have finished basic facts about Pareto distribution. Thank you.